What was there before time, space, and matter existed? This is one of the deepest questions humanity has ever asked. If we look around us, everything we see, the galaxies, the stars, the planets, even ourselves, seems to have a common origin, a first moment when everything began. But how can the entire universe, with its countless forms and mysteries, arise from an unknown initial state? And how can we, from our small corner of the cosmos, trace that primordial moment? Sometimes, trying to understand the origin of the universe feels like trying to read the first chapter of a book whose cover is sealed. However, science has managed to open a small window to that distant past. How close can we get to the moment when everything began? What does physics tell us about that zero time when current laws cease to make sense? It is fascinating to think that all the matter that makes up the stars, the oceans, and our own bodies was once compressed into a state so dense and hot that it defies our imagination. For generations, humans have sought answers by observing the night sky. We have invented myths, developed mathematics, and built telescopes capable of looking through billions of light years. But even with the most modern advancements, we still face puzzling enigmas. Why is the universe expanding? Why is there something instead of nothing? What clues do the oldest light, invisible radiation, and elementary particles offer us about that first moment? Understanding the Big Bang is not just a matter of physics or astronomy. It is an exploration that challenges our concepts of time, space, and reality. It is the story of how, from an unimaginable beginning, everything we know emerged. Today, we will embark on a journey to that origin, to the moment when the universe, as we understand it, took its first step. Are we really ready to discover how it all began? What is the Big Bang really? When we hear those words, many think of a great explosion that filled the void with matter and energy. But was the Big Bang a conventional explosion, like a bomb detonating in space? Not exactly. The Big Bang is much more surprising. It is the name we give to the moment when space and time, along with all the matter and energy of the universe, began to expand from an extremely dense and hot state. There was no explosion at a specific point in space. Rather, space itself was being created and expanding in all directions at the same time. Can we imagine what that initial moment was like? Physics describes that moment as a singularity, a situation where the laws we know cease to make sense. All matter, all energy, even space and time themselves, were compressed into an unimaginably small state. But instead of remaining that way, that singularity began to expand rapidly. Why did this happen? It is one of the great questions of modern science, and although the details still elude our complete understanding, what we know is that this event marked the origin of everything that exists. The Big Bang Theory is not just an abstract idea. It is the best supported scientific explanation for the origin of the universe. How do we know this? Because through decades of observation and experimentation, astronomers have found compelling evidence. The ongoing expansion of the universe, the cosmic microwave background radiation, and the abundance of light elements, for example. All this data fits together like pieces of a huge cosmic puzzle, pointing to a single origin: the Big Bang. Does this mean that the Big Bang explains absolutely everything? Not exactly. The theory explains how the expansion began, but not what happened before or why it happened. It also doesn't tell us why there is something instead of nothing. However, what is fascinating is that, although there are still mysteries to solve, the Big Bang offers us the best window to observe the birth of the universe and understand how, from a primordial state, stars, galaxies, and ultimately ourselves emerged. What exactly is the observable universe? Why can't we see the entire universe, but only a limited portion? The answer lies in the speed of light and the time that has passed since the origin of the cosmos. Light travels at a finite speed, approximately 300,000 kilometers per second, and we can only receive information from objects whose light has had enough time to reach us since the beginning of the universe. If the cosmos is estimated to be nearly 14 billion years old, then, in theory, the farthest distance from which we could see something would be 14 billion light years. But this is where the universe surprises us. It turns out that, due to the expansion of space, that edge of the observable universe is much farther away than what simple multiplication of age by speed suggests. Today, the radius of the observable universe is about 46 billion light years. How is this possible? Because while the light was traveling towards us, space itself was expanding, stretching the distances. It's like throwing a bottle into the sea, and as it floats towards the shore, the tide pushes the water and the bottle further away. That's why the observable universe is a bubble, a gigantic sphere around us, with us at the center, not because we are special, but because it is from where we observe. Does this mean that the universe ends at that edge? Absolutely not. The observable universe is simply the portion of the cosmos from which light has managed to reach us since the Big Bang. Beyond that limit, the universe continues, possibly infinitely, but those places are inaccessible to us, at least for now. What lies outside the observable universe remains hidden, as if it exists in a neighboring room that we can never enter, not even peek through the keyhole. This limit is not a physical wall, but a boundary imposed by the laws of physics and time. Every distant galaxy we see is like a postcard from the past. The farther we look, the further back in time we see. Some galaxies we observe today no longer exist or have completely changed, but their light continues to travel towards us. The observable universe is, in a sense, a natural time machine, allowing us to reconstruct cosmic history, although always with the certainty that there is much more beyond what we will ever be able to see.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey.
Has the universe always been the same size? This is one of the most fascinating questions science has asked, and the answer is surprising. The universe is not static, it is growing. Since its origin, space itself has been expanding, like a loaf of bread rising in the oven, where the raisins are the galaxies moving away from each other. But what does it really mean that the universe is expanding? It's not that galaxies are moving through empty space, but rather that the space between them is stretching, causing distances to increase over time. This phenomenon was a revolution in our understanding of the cosmos. Before, most people thought the universe was unchanging and eternal, but the discoveries of the 20th century changed that view forever. When astronomers observed distant galaxies, they noticed that their light was redshifted, an unmistakable sign that they are moving away. This effect, known as redshift, is similar to what happens when an ambulance moves away and its siren sounds lower. It is direct evidence that the universe is expanding in all directions. Is there a center from which everything is moving away? The answer is even stranger. There is no center of the universe. The expansion occurs at all points in space simultaneously. No matter where you are, you will see that all galaxies, except for a few neighbors, seem to be moving away from you. It's as if you were on the surface of an inflating balloon. From every point, the other points are moving away. But there is no center on the surface itself. How much has the universe expanded since its origin? Astronomers estimate that the observable universe today has a diameter of about 93 billion light-years, even though it originated from a region much smaller than an atom. And the most astonishing thing, the expansion is not slowing down. It is accelerating. Why is this happening? The cause is still a mystery, although it is suspected that something called dark energy, a mysterious force, is pushing the universe to expand faster and faster. Thus, the expansion of the universe not only reveals its past, but also raises new questions about its future and the ultimate fate of everything that exists. What led astronomers to suspect that the universe was not static, but rather changing on a large scale? At the beginning of the 20th century, the prevailing view was that the cosmos was unchanging, eternal, and fixed. However, all of this changed thanks to a man named Edwin Hubble and an observation that, at the time, seemed merely a curiosity: the redshift of light from galaxies. Hubble, using one of the most powerful telescopes of his time, observed that many galaxies showed spectral lines shifted towards the red end of the spectrum. But what does that really mean? To understand it, let's think about the Doppler effect, that phenomenon you notice when an ambulance approaches and then moves away from you. The sound of the siren changes pitch. With light, something similar happens. When a luminous object moves away, its light gets stretched and becomes redder. Hubble discovered that the farther away a galaxy was, the greater this redshift. Why do all these galaxies seem to be fleeing from us? Are we at the center of the universe? The answer is even more fascinating. It's not that the galaxies are moving away from a fixed point, but that the very space between them is expanding, as if the universe were a loaf of bread in the oven and the raisins inside were separating as the dough rises. Hubble's discovery was revolutionary. By analyzing the data, he established a direct relationship between the distance of a galaxy and the speed at which it is moving away from us. This is known today as Hubble's law. In short, the farther away a galaxy is, the faster it seems to be receding. Is this just a coincidence? No. It is the best evidence that the universe is expanding. This simple pattern observed in the redshift is perhaps one of the most compelling pieces of evidence that the universe had a beginning and has been growing ever since. But how did this change our place in the cosmos? The expansion of the universe implies that, if we go back in time, all matter and energy were once concentrated in an extremely dense and hot point. Hubble's observation not only shattered the idea of a static universe, but also laid the groundwork for the concept of the Big Bang. Thus, by looking at the light from distant galaxies, we find clues about the universe's remote past and how, from the simple observation of red light, one of the deepest ideas in science emerged. The universe has a history, and we can read it. What if I told you there is a signal, an invisible echo, that travels throughout the universe, carrying with it the story of its origin? This signal is the cosmic microwave background radiation, a true cosmic fossil. But what is it exactly and why is it so important? To understand it, let's think of the universe as a room that was once filled with hot, glowing fog. Over time, that fog cooled and dissipated, but it left behind a faint glow, a kind of thermal whisper that we can still detect today with very sensitive antennas. The cosmic microwave background radiation is the oldest light we can observe. It originated when the universe was just a few 100,000 years old, and the temperature was so high that matter and light were trapped in a constant embrace. But at a crucial moment, protons and electrons joined to form atoms, and light was freed to travel. That same light, stretched by the expansion of the universe, now reaches us in the form of microwaves, so cold that their temperature hovers around 2.7 degrees above absolute zero. It's as if the universe left a nightlight on to remind us of its childhood. Why do scientists consider this radiation as key evidence of the hot and dense origin of the cosmos? Because its existence and characteristics fit perfectly with the predictions of the Big Bang theory. If the universe had begun in any other way, we wouldn't find this homogeneous microwave background filling space. In fact, its accidental discovery in the 1960s solved one of the greatest mysteries of cosmology and became one of the strongest pieces of evidence that the universe indeed had an extremely hot beginning. Moreover, the cosmic microwave background radiation is not completely uniform. It presents tiny temperature fluctuations, variations as small as 1 part in 100,000. Why is this fascinating? Because those small differences are the seeds of all the structure we see today: galaxies, clusters, and ultimately, ourselves. Those irregularities reveal the traces of the physical processes that occurred in the early moments of the universe, allowing astronomers to reconstruct cosmic history almost like detectives studying an ancient scene for crucial clues. In summary, the cosmic microwave background radiation is much more than a distant echo. It is the oldest photograph of the universe and the tangible proof of a common origin for all the matter and energy that exists today. Every time scientists fine-tune their instruments to analyze this cosmic background, they are looking directly into the most remote past, to the moment when darkness was filled with light for the first time. Is there a more impressive time capsule than that? What exactly is the standard model of the Big Bang, and why does the scientific community place so much importance on it? This theory is the framework that best describes the origin, evolution, and structure of the known universe. But it's not just about a gigantic explosion from nothing. The Standard Model tells us that the universe began about 13.8 billion years ago in an extremely hot and dense state, and has been expanding and cooling ever since. It's as if all the energy and matter of the universe were compressed into an incredibly tiny point, and suddenly that energy was released, marking the beginning of everything that exists. But how do we know that this model is more than just a simple idea? The key lies in its ability to explain and predict observed phenomena. For example, why is the universe filled with hydrogen and helium, and there is barely any lithium? Why is space permeated by a faint microwave radiation that seems to come from all directions? The Standard Model answers these questions by describing how, in the first minutes, the lightest elements formed from the primordial soup of particles, and how, hundreds of thousands of years later, light was able to travel freely through the cosmos, leaving that fossil echo that we still detect today. Another curiosity: why does the universe look so uniform everywhere, yet at the same time show small irregularities that gave rise to galaxies and stars? The Standard Model incorporates the idea of accelerated expansion in the first moments, known as inflation, which explains this surprising combination of homogeneity and slight fluctuations. It's as if the universe was rapidly inflated, smoothing out wrinkles but leaving small seeds that, over time, would grow into clusters and galaxies. Of course, no model is complete without open questions. The Standard Model of the Big Bang accurately describes the evolution of the observable universe, but still leaves enigmas. What exactly happened at the initial moment? Where do dark matter and dark energy come from, which dominate the universe but remain invisible? Despite these unknowns, this model has withstood decades of testing and observations, and remains the best scientific explanation for the origin and development of the cosmos, paving the way for new questions and discoveries. What does zero time really mean? Scientists use this term to refer to the exact moment when, according to the Big Bang theory, the universe began. But can we imagine that moment? Zero time is such an extreme concept that it actually escapes human understanding and current mathematics. It is the point at which the universe, matter, energy, space, and even time itself originated. Before that moment, there simply was nothing that could be defined as before. How is it possible that there is a before time? It is a question that challenges everyday logic. In physics, zero time corresponds to what we call a singularity, a region where the known laws of nature cease to function. There, the density and temperature of the universe would be infinite, and everything we know would be compressed into a point of unimaginable size. Can we visualize this? Not really. It's like trying to fit all the oceans of the Earth into a cup. It simply makes no sense. The singularity of zero time is not only a challenge for our imagination, but also for science, because the equations of general relativity, which perfectly explain the universe on a large scale, break down when reaching that point. On the other hand, quantum mechanics, which describes the world of the very small, also cannot explain what happens there, because it is not unified with gravity. If zero time represents an absolute limit for physics, What can we say about the universe just after that moment? In the fractions of a second following zero time, the universe began to expand and cool rapidly. But the exact moment of origin, that first tick of the cosmic clock, remains shrouded in mystery. The inevitable question is, did zero time really exist as we imagine it? Or is it just the edge of our understanding, a frontier beyond which we cannot look? Some scientists think that, in reality, there was never an absolute zero point, but rather that time and space emerged together from an even more fundamental reality, perhaps governed by unknown rules. Will we ever know what happened in that first instant? To answer this, physics needs a theory capable of unifying relativity and quantum mechanics, a theory of quantum gravity. Without it, zero time remains a closed door, an enigma at the crossroads of knowledge and imagination. Despite all the advances, the birth of time is one of the deepest questions facing humanity. Zero time is, so far, a reminder that the universe still holds impenetrable secrets at its origin. What happened in the first moments after the origin of the universe? To answer this, we must travel to a realm where the laws of physics, as we know them, brush against the limits of the imaginable. We are talking about the first moments after the cosmic beginning, a span so brief that it is almost incomprehensible. In less than a 10 millionth of a trillionth of a second, the universe expanded and evolved with a violence and speed impossible to experience in everyday life. Why is this interval so important? Because in those fleeting moments, the foundations of everything that exists today were established. At first, the universe was unimaginably dense and hot, with temperatures exceeding anything we can recreate on Earth. If the universe were a movie, these first frames would be almost impossible to distinguish due to their speed. In the fraction of time known as Planck time, approximately 100 billionth of a trillionth of a second. Gravity, the strong nuclear force, the weak nuclear force, and electromagnetism may have been unified into a single force. No one can know exactly what happened at that moment, but physicists believe that a single soup of energy governed all of space. But how did the universe transition from that chaotic initial state to one where physical laws begin to make sense? Shortly after this first instant, an astonishing event occurred, the accelerated expansion known as inflation. In a tiny span, the universe expanded much faster than the speed of light, multiplying its size in a fraction of a second. To imagine it, think of inflating a balloon so quickly that it goes from invisible to the size of a galaxy in less time than it takes to blink. Why was this crucial? Because inflation smoothed out the universe, eliminating wrinkles and allowing matter and energy to be distributed almost perfectly everywhere. At the end of inflation, the energy driving this expansion transformed into a rain of fundamental particles. Quarks, electrons, neutrinos, and photons appeared, although atoms and stars did not yet exist. How dense and hot was everything? In these early moments, a teaspoon of the universe would contain more mass and energy than all the mountains on Earth combined, and the temperature exceeded 100 billion degrees. Amid this storm, particles collided, were created, and annihilated each other in a frantic dance dominated by pure energy. Did the transformation stop there? No. As microseconds passed, the universe continued to expand and cool. In less than a second, quarks began to combine to form protons and neutrons, the building blocks of atomic nuclei. This process marked the beginning of complexity. From simple ingredients and extreme physics, the cosmos began to organize itself. Thus, in the first fractions of a second, the fate of the universe was sealed, the seeds of matter were created, and the evolution that, billions of years later, allows us to question our own origin was set in motion. What if the universe had grown faster than the speed of light in its first moments? This is the surprising idea behind the theory of cosmic inflation. According to physicists, in a tiny fraction of a second after the origin of the cosmos, space expanded exponentially, astonishingly multiplying its size. It wasn't a normal growth. It was as if a speck of dust inflated to the size of a galaxy in less time than it takes for light to blink. Why do scientists defend such an extreme idea? The answer lies in the problems that inflation solves and the traces it has left in the universe. One of the great enigmas was the astonishing balance and uniformity of the cosmos. If we look in any direction, the cosmic microwave background, that faint glow remaining from the origins, has practically the same temperature everywhere. But according to the normal laws of physics, such distant regions wouldn't have had time to agree, to exchange light or information, to achieve that uniformity. Cosmic inflation resolves this mystery. Before the brutal expansion, everything was so close that it could equalize, and then suddenly, the universe stretched, causing those already balanced regions to be separated by immense distances. And what about the structure of the universe? Why do clusters of galaxies, voids, and cosmic filaments exist? Inflation also answers this question. During that fleeting moment of accelerated growth, quantum fluctuations, tiny variations in energy density, inflated to become the seeds of all cosmic structure. It's as if small wrinkles on a balloon, when suddenly inflated, transformed into mountains and valleys on its surface. Today, the patterns we observe in the distribution of galaxies and in the background radiation are the echoes of those amplified fluctuations during inflation. But what really caused this dramatic event? Scientists propose the existence of a hypothetical field called the inflaton field, which would have triggered inflation. This field contained a tremendous amount of energy, and by releasing that energy during the expansion, the universe cooled and allowed for the formation of particles and forces as we know them today. Although the inflaton remains a mystery, its effect is consistent with the most precise observations made to date. Cosmic inflation is one of the boldest and most fascinating ideas in modern cosmology. It not only solves several fundamental problems, but also predicts details that we have been able to verify with telescopes and satellites. However, the exact mechanism that originated it remains one of the great open questions in physics. Was inflation a unique event, or could it repeat in other regions of the cosmos, giving rise to other universes? Although the answer still eludes us, inflation remains the best explanation we have for understanding how such a vast, structured, and uniform universe could arise from such a small and chaotic beginning. In the early moments of the universe, long before galaxies, stars, or even atoms existed, everything we know was immersed in a chaotic and extreme state. What was that environment like where it all began? Scientists call it the primordial soup, and it's not a light metaphor. It's literal, though very different from any broth we've ever tasted. In this soup, the universe was an incredibly dense and hot mix of elementary particles, pure energy, and radiation. Imagine a pressure cooker where the fundamental ingredients of matter are boiling at temperatures of billions of degrees, a situation so energetic that even protons and neutrons could not yet form. What ingredients were in this cosmic recipe? Back then, we found quarks, electrons, neutrinos, and photons, all interacting frantically in a sea of energy. Quarks, for example, are particles so small that they cannot be seen even with the most powerful microscopes, but they are essential because they will later combine to form protons and neutrons. Why didn't they join together at that moment? The answer lies in the temperature. It was so high that any attempt by the quarks to group together was quickly destroyed by energetic collisions. It's like trying to build a house of cards in the middle of a hurricane. And what role did light play in all this? Photons, the particles of light, were everywhere, but unlike what happens today, they could not travel freely. Every time a photon tried to move forward, it collided with electrons and other particles, being absorbed or deflected. The universe was opaque, a thick fog in which light could not escape. This state was so dense and hot that matter and energy were practically fused, with no way to distinguish one from the other. But how long did this primordial soup exist? Although it may seem incredible, this period lasted only a tiny fraction of a second, but it was crucial for everything that came afterward. In that brief moment, the foundations for the formation of matter as we know it were laid. The laws of physics that govern our universe emerged amid this chaos, allowing, as the soup cooled a bit, for the ingredients to begin to organize. Thus, from this cosmic broth, the first structures emerged that, much later, would give rise to atoms, stars, and planets. The primordial soup was the stage where matter and energy danced their first great waltz, marking the true beginning of the history of the universe. What happened when the universe was just a fraction of a second older than time itself? If we could go back to those first moments after the Big Bang, we would find ourselves in a completely different scenario than the one we know today, a boiling and chaotic ocean, where matter as we understand it did not yet exist. The temperature was unimaginably high, with pure energy constantly transforming into elementary particles and their opposites, antimatter, in an almost instantaneous process. In that extreme environment, nature was playing at building the fundamental bricks of everything that exists. But what exactly are these elementary particles? They are the most basic components of matter, such as quarks, electrons, and neutrinos. During those first moments, quarks floated freely, unable to combine to form protons or neutrons due to the prevailing thermal violence. It was like trying to build sandcastles in the middle of a storm. Any attempt at joining was quickly destroyed by the surrounding energy. Electrons and neutrinos, for their part, also wandered alone, with no possibility of forming atoms or molecules. As the universe expanded, the temperature began to drop rapidly. This decrease allowed quarks to start grouping into threes, forming protons and neutrons, the first nuclei of what would later become atoms. Why threes? Because the strong force, one of the four fundamental forces of the universe, acts like an incredibly powerful glue that only allows specific groupings of quarks, giving stability to these new particles. It is at this moment that the universe stops being a soup of isolated particles and begins to organize itself, laying the foundations for complex matter. However, an intriguing question arises. If energy could create particles and antiparticles equally, why do we see a universe made almost exclusively of matter today? The answer is that, in that primordial chaos, for every billion pairs of matter and antimatter, there was one extra particle of matter. When matter and antimatter encountered each other, they annihilated one another, releasing energy. Only that small surplus of matter survived, and with it, everything we know: galaxies, stars, planets, and ourselves. Thus, from a sea of energy and unimaginable chaos, the first particles emerged, the foundations of the reality we inhabit. What if you could travel back in time to the first minutes after the origin of the universe? In that extraordinary period, the cosmos was a seething mix of protons, neutrons, electrons, photons, and neutrinos, all interacting in a frantic dance at unimaginable temperatures and densities. But how did we go from that primordial chaos to the emergence of the simplest elements that today form stars, planets, and ultimately ourselves? The answer lies in the synthesis of light nuclei, a key process that shaped the chemical fate of the universe. During the first 3 minutes, the temperature of the universe dropped enough for protons and neutrons to begin to combine. Before that moment, the energy was so high that any attempt to form nuclei was quickly destroyed by the impacts of energetic particles, as if you were trying to build a house of cards in the middle of a hurricane. But as the universe expanded and cooled, conditions changed. Why were only some elements formed and not others? The answer lies in nuclear physics and the balance between the speed of reactions and how quickly the universe was cooling. The first step was the formation of deuterium, a nucleus composed of one proton and one neutron. However, deuterium was extremely fragile, and for a few moments, any deuterium that formed was immediately destroyed by high-energy photons. Only when the universe cooled sufficiently could these nuclei survive long enough to fuse and give rise to more complex nuclei, such as helium and lithium. Thus, in a matter of minutes, nearly 3/4 of the matter became hydrogen, and about 1/4 became helium, with tiny traces of lithium. Isn't it fascinating to think that the basic composition of the universe was established in such a short time? Why weren't heavier elements formed at that stage? The reason lies in the absence of stable nuclei with 5 or 8 nucleons, which prevents the direct formation of elements like carbon or oxygen in this primordial process. It was as if nature had built a staircase with some missing steps, making it impossible to continue ascending to more complex nuclei. Heavier elements would have to wait for the emergence of the first stars, where conditions would be very different. The result of light nucleus synthesis not only determined the abundance of hydrogen and helium in the universe, but it also provides us with one of the strongest pieces of evidence for the hot and dense origin of the cosmos. Today, when we analyze the ratio of these elements in space, we find exactly what this theory predicts. Thus, the first minutes after the origin of the universe left an indelible chemical mark, a kind of cosmic birth certificate that we can still read billions of years later. What does it mean that the universe had an era dominated by radiation? To answer this, we must first imagine the universe in its infancy, when it was so extremely hot and dense that energy and matter existed in a kind of constant battle. In those first hundreds of thousands of years, radiation, that is, light and other forms of electromagnetic energy, played a much more prominent role than matter. But why does this happen? The key lies in how energy and matter behave when the universe is small and hot. Radiation contains more energy per volume than matter, and moreover, moves at the speed of light, while matter particles are much slower. Have you ever wondered what it was like to live in a universe where light was more important than atoms? During the radiation era, particles of light, or photons, not only abounded but dominated events. Matter, made up of protons, neutrons, and electrons, existed, but it was like small boats floating in a sea of pure energy. Every time a matter particle tried to join with another, radiation would strike it and separate it again, preventing the formation of stable structures. During this period, temperatures were so high that even atomic nuclei struggled to stay together. How long did this dominance of radiation last? The universe continued to expand and cool, and at some point, matter began to gain ground. Why? Because while radiation loses energy with the expansion of space, matter simply separates but retains its mass. Thus, over time, the energy density of radiation fell faster than that of matter. This may seem strange, but it's like having two types of balloons, one filled with steam and the other with lead pellets. As the balloon expands, the steam cools and disperses faster than the pellets. Similarly, the energy of radiation dilutes and loses strength before matter does. At what point did matter take control? Approximately when the universe was about 70,000 years old, matter began to dominate over radiation. That change was fundamental for the development of the structures we know today, such as galaxies and stars. During the radiation era, the universe was a turbulent ocean of energy, where light was the absolute queen and matter barely a supporting actor. But as expansion continued, matter took the leading role, and the universe began to resemble the one we inhabit today. The era of radiation is, in essence, the story of how light ruled the cosmos before yielding the throne to matter. What if I told you that there was a moment in the universe when light could not travel freely? For hundreds of thousands of years after the cosmic origin, the universe was an opaque place, where light was trapped as if it were in the midst of a dense fog. Why did this happen? The answer lies in the intimate relationship between light and matter. At that time, the universe was so hot and dense that electrons and protons were separated, forming a plasma. Every photon, that is, every particle of light, constantly collided with these charged particles, unable to advance more than a tiny fraction of a centimeter before being deflected. But then, something extraordinary happened. When the universe was about 380,000 years old, the temperature dropped enough for protons and electrons to combine and form hydrogen atoms. This process, known as recombination, changed everything. With no free electrons in abundance, photons were no longer scattered at every turn. It was as if, suddenly, the fog dissipated and light could finally travel unobstructed through space. What does this phenomenon look like? Imagine a room filled with smoke so thick that you can't see your own hand. Suddenly, the smoke disappears and the room is completely clear. That was the decoupling of light, the first time photons could traverse the cosmos without being stopped. The light released at that moment still exists today, traveling through space, and we detect it as the cosmic microwave background radiation, a kind of fossil echo of the primitive universe. Why is this event so crucial? Because it marked the moment when the universe became transparent and luminous information could begin to travel to us. Everything we know about the origins of the cosmos, we know thanks to the light that decoupled at that moment. It's as if the universe had turned on its first beacon, and since then, that light allows us to look back to the most distant past, just a few 100,000 years after the beginning of it all. For hundreds of thousands of years, the universe was a blazing ocean of particles and radiation, too hot for atoms to exist. But what had to happen for the first atoms, the fundamental building blocks of everything we know, to form from that chaos of energy and loose particles? The answer lies in a decisive phenomenon known as recombination. As the universe expanded, it also slowly cooled. When the temperature dropped to about 3,000 degrees Kelvin, something extraordinary became possible for the first time. Protons and electrons could join together to form neutral hydrogen atoms without being immediately separated by the energy of photons. Why is the formation of atoms so crucial? Without atoms, there would be no stars, no planets, and no ourselves. During this period, free electrons finally found a home by joining with nuclei, primarily protons. It was as if the universe, which had previously been a room full of people running chaotically, finally allowed each person to find a chair. Before this, light could not travel freely, as it was constantly scattered by loose electrons. But with the emergence of atoms, light became free, ushering in a new era of cosmic transparency. Did you know that most of the atoms formed at that time were hydrogen, the simplest and most abundant element in the universe? A small fraction of helium and traces of lithium were also formed, but hydrogen overwhelmingly dominated. This process not only allowed light to travel through space, but also laid the chemical foundations for the formation of the first stars and galaxies long after. From then on, the universe ceased to be opaque and became transparent, allowing the cosmic microwave background radiation, the echo of the Big Bang, to reach us billions of years later. Was the formation of atoms instantaneous? In reality, it was a gradual process, stretching over hundreds of thousands of years. Little by little, matter ceased to be a chaotic plasma and became a gas of neutral atoms. Without this transformation, the universe would remain a dark and disordered place, incapable of giving rise to complex structures. Thus, the formation of the first atoms marked the beginning of a new stage, the possibility that one day stars, planets, and ultimately life itself could exist. What happened in the universe when the first lights went out? After the intense initial flash and the formation of the first atoms, the cosmos entered an enigmatic stage known as the cosmic night. Why do we call it that? For hundreds of millions of years, the universe was shrouded in absolute darkness. There were no stars, no galaxies, no sources of light to illuminate the vast ocean of space and time. There was only a haze of hydrogen and helium gas, slowly cooling as it floated through the abyss. This period raises a fascinating question. If the universe was full of matter, why did darkness prevail? The answer lies in the transparency of the cosmos. After electrons and protons formed the first atoms, light could, for the first time, travel freely. However, there were still no stars or galaxies lit up to produce new flashes. It was as if the curtain of the stage had been lifted, but the spotlights were still off. In that immense cosmic theatre, matter was silently gathering, preparing for the grand shows of the future. Was it really a total void? Not exactly. Although at first glance it might seem that nothing was happening, gravity was silently at work, gathering small fluctuations of matter into increasingly dense clouds. If we could travel back in time to that moment, we wouldn't see anything, but we would be witnessing the delicate movements that, over time, would give rise to everything we know today. The cosmic gas was so cold and uniform that any small variation was crucial. Those minimal differences in density would be the seeds of future stars and galaxies. How long did this primordial night last? Surprisingly, this dark period extended for hundreds of millions of years. Only when matter condensed enough and gravity ignited the first stellar fires did the darkness begin to dissipate. It was then that light flooded back into the universe, marking the end of the cosmic night and the beginning of a new era filled with structures, colors, and energy. This silent stage, though invisible, was absolutely essential. Without it, the universe would never have had the necessary conditions for stars, galaxies, and ultimately, us to emerge. How is it possible that the universe, which began as a hot and uniform soup of particles, ended up filled with stars shining in the darkness? To answer this, we must first understand that, although the cosmos was almost perfectly uniform, there were tiny fluctuations in density, like small wrinkles in a freshly laid sheet. Those regions, slightly denser than their surroundings, began to attract neighboring matter thanks to gravity, the great cosmic sculptor. What happens when these small differences grow? They become the seeds of the first structures, the places where, millions of years later, the first stars would be born. But when did these pioneering stars actually emerge? Astronomers estimate that the first stars appeared a few 100 million years after the origin of the universe, when the matter accumulated in those dense regions reached the sufficient mass to initiate a fascinating process. Under the tremendous pressure of gravity, the gas, composed almost entirely of hydrogen and helium, began to collapse and heat up. Thus, in the heart of these clouds, the temperature rose to tens of millions of degrees. Why is this important? Because it is precisely at that point that nuclear fusion can ignite. Hydrogen atoms fuse to form helium, releasing an enormous amount of energy. In that instant, the first star ignites. How did these stars differ from those we see today in the sky? The first stars, known as population 3 stars, were true giants. Many of them had masses tens or even hundreds of times greater than the Sun and lived brief but intense lives. Lacking heavier elements than helium, their formation and evolution were very different from current stars, which are already born enriched with the elements produced by previous generations. These colossal stars illuminated the universe for the first time, breaking the cosmic darkness and initiating the so-called reionization, a process that allowed the universe to cease being opaque to light. Why are these first stars so crucial in the history of the cosmos? Because they acted as factories of elements. When these massive stars exhausted their fuel, they exploded as supernovae, scattering the first atoms of carbon, oxygen, and other heavy elements into space. Thanks to them, the universe ceased to be a simple place and became capable of forming planets, life, and ultimately ourselves. The birth of the first stars was the decisive step that transformed a dark and simple universe into a luminous and complex one, sowing the seeds of everything we know today. How did the first galaxies form in a universe that was just beginning to organize itself? After the emergence of the first stars, gravity played its mastercard. It attracted and grouped enormous amounts of gas and dark matter into vast clusters. But why didn't matter distribute evenly across the cosmos? The answer lies in the tiny density fluctuations that existed from the very origin of the universe. Like small wrinkles on a perfectly stretched sheet, these irregularities served as seeds for matter to concentrate at certain points and initiate the process of galaxy formation. The first galaxies bore no resemblance to the majestic spirals that populate the universe today. They were irregular, chaotic structures, much smaller, composed of young, hot stars clustered together. What held these proto-galaxies together? The answer lies in gravity, a force as patient as it is relentless, which shaped and merged these galactic embryos over hundreds of millions of years. Gradually, collisions and mergers between these small galaxies gave rise to larger and more complex systems. In a way, the universe was like a huge workshop, slowly assembling the pieces we now recognize as fully formed galaxies. But how do we know when and how these first galaxies appeared? Astronomers have managed to observe light coming from times close to the birth of the universe, using telescopes so powerful they function like true time machines. By analyzing these signals, they have discovered that the first galaxies emerged approximately between 500 million and 1 billion years after the origin of the cosmos. This light, very faint and redshifted, reveals to us that the first galaxies were places of frenetic activity, where star formation was much more intense than it is today. In fact, it is estimated that some of these galaxies were forming new stars at a rate up to 100 times greater than that of the current Milky Way. Why is it so important to understand the emergence of the first galaxies? Because in them, the heavier elements were forged, and the fundamental structures of the universe were established. Without these first islands of matter, the galactic clusters, filaments, and voids that make up the cosmic architecture simply would not exist. Each primitive galaxy was like a laboratory of nature, where gravity, matter, and energy interacted to give rise to the complexity we observe today. Ultimately, the emergence of the first galaxies marked the true beginning of the grand cosmic story, setting the stage for everything that would exist afterward, from planetary systems to life itself. What happens when a universe that has just been born, after millions of years of darkness, lights up again, as if someone turned on the lights for the first time? We know this transformative phenomenon as the reionization of the universe. But why is this episode so important, and what mystery does it hold? To understand it, we must first imagine a cosmos shrouded in twilight, filled with neutral hydrogen atoms that absorb light, preventing it from traveling freely. It was the so-called dark universe, a time when light could not travel great distances. So, what changed this scenario and allowed the universe to become transparent? The key lies in the first stars and galaxies. When they began to form, they released colossal amounts of ultraviolet radiation. That energy was enough to strip hydrogen atoms of their electrons, a process that turned them into charged particles, or plasma. It's as if the radiation from the stars had awakened the hydrogen, causing it to stop absorbing light and allowing photons to travel freely. Why do we call this reionization? Because after the birth of the universe, hydrogen had already been ionized before recombining into neutral atoms. Now, thanks to the light from the first stars, it was ionized for a second time. But how long did this process last, and what traces did it leave? Reionization did not happen overnight. It stretched over hundreds of millions of years. At first, ionized bubbles formed around the first luminous sources, and over time, those bubbles grew and merged until most of the hydrogen in the universe became ionized. Astronomers have managed to see fragments of this process by studying the light from very distant galaxies and the shadow that neutral hydrogen leaves in its path toward us. The study of reionization is like reading the universe's diary, as it reveals when and how the first complex structures began to modify their environment. Why should we care about this process? Reionization marked the transition from an opaque universe to a transparent one. Without it, the light from stars and galaxies would never have reached us, and the cosmos would still be wrapped in an impenetrable fog. This phenomenon determined the conditions for the formation of everything that came after: galaxies, clusters, planets, and ultimately, life. Understanding reionization is answering the question of how the universe managed to emerge from darkness and become visible. It is the chapter in which the cosmos, after its long night, finally sees the light. How is it possible that, at first glance, the universe appears chaotic and disordered? Yet when we analyze it on a large scale, it reveals a surprising organization. If we could move billions of light years away, we would see that galaxies are not distributed randomly, but rather form a kind of cosmic web. This gigantic spider web is made up of filaments of galaxies, clusters, and enormous voids, as if the cosmos were playing at designing an invisible yet precise structure. Why does the universe take on this peculiar shape, and what does it reveal about its history and composition? Galaxies tend to gather in clusters, which in turn group into superclusters, connected by filaments that stretch across hundreds of millions of light years. Between these filaments are nearly empty regions, called cosmic voids, where there are hardly any galaxies. It's as if the universe were a colossal sponge. Matter, concentrated in the walls and edges, leaves vast gaps in the interior. This structure, known as the cosmic web, is one of the most astonishing discoveries of modern cosmology. But how did the cosmos come to organize itself in such an intricate and symmetrical way? The key lies in the small density fluctuations that existed in the primitive universe. These tiny differences, almost imperceptible, were amplified over time by gravity. Where there was a little more matter, gravitational attraction accumulated even more, thus forming the seeds of future clusters and filaments. Over billions of years, these dense regions grew and transformed into the structures we observe today, while the voids expanded and became virtually devoid of galaxies. In a way, the universe behaved like a loaf of bread fermenting. Small bubbles within the dough expand to form a network of gaps and walls. The most fascinating part is that visible matter, such as stars and galaxies, represents only a small fraction of this structure. The true architecture of the universe is dictated by dark matter, an invisible substance that acts as the scaffolding upon which galaxies and clusters are built. Without it, the cosmic web could not have formed as we see it today. How far does this web extend? Studies show that it stretches far beyond what we can observe, suggesting that large-scale structure is a fundamental feature of the universe as a whole. Thus, the apparent disorder of the cosmos hides a deep and elegant order, the result of forces and processes acting on unimaginable scales. What really holds the universe together? This question leads us to one of the greatest mysteries of cosmology: dark matter. Everything we see around us, from stars to galaxies, represents only a small fraction of what makes up the cosmos. But then, what keeps those galaxies together, preventing them from disintegrating due to the speed at which they spin? The answer seems to lie in an invisible substance, directly undetectable, but whose influence is impossible to ignore. Although we cannot see dark matter or touch it, its presence reveals itself in surprising ways. For example, when we observe the movement of galaxies, we find that the stars at their edges move much faster than they should if only visible matter existed. It's as if an invisible force acts like glue, keeping the structure of galaxies cohesive. This phenomenon is so strange that, without dark matter, galaxies would simply crumble, unable to withstand the centrifugal force of their own rotation. But how much dark matter is there really? Astronomers estimate that about 85% of all the matter in the universe is dark matter. This means that everything we can see, measure, and analyze directly, planets, stars, gas, dust, is barely the tip of the iceberg. The rest, this invisible skeleton, shapes the architecture of the cosmos on a grand scale. Without dark matter, there would be no galaxy clusters, no filaments connecting the densest regions of the universe, and no enormous bubbles of vacuum between them. The big question is, what is dark matter? To this day, no one knows for sure. It neither emits nor reflects light, does not interact with electromagnetic radiation, and we only detect it through its gravitational effect. Many hypotheses have been proposed, from exotic particles like WIMPs or axions, to theories suggesting that perhaps our understanding of gravity needs to be revised. The search for dark matter is one of the most fascinating scientific adventures of the 21st century, because understanding its nature could reveal profound secrets about the origin and fate of the universe. Could a universe exist without dark matter? Evidence suggests that, in a cosmos without that invisible skeleton, ordinary matter would never have formed complex structures. There would be no galaxies, no stars, no planets. In a sense, dark matter is the scaffolding upon which everything we know is built. Thus, although it remains hidden, its footprint is indelible, and its existence is fundamental for the universe to be as we observe it today. Has the universe always expanded at the same rate? For a long time, scientists thought that gravity would slow down cosmic expansion. But in the late 20th century, a puzzling observation changed everything. The expansion of the universe not only continues, but is accelerating. What mysterious force could be pushing galaxies to separate faster and faster, as if the universe had its foot on the gas pedal? The answer, or at least the name we've given to this enigma, is dark energy. Dark energy is one of the greatest mysteries of modern physics. Although we cannot see or touch it, astronomers deduce its existence from its gravitational effects on a large scale. When scientific teams studied distant supernovae, they expected to find that the universe was slowing down. Instead, they discovered just the opposite. The supernovae were farther away than expected, which could only be explained if something invisible was accelerating the fabric of space-time. To visualize it, imagine throwing a ball upward and, instead of slowing down and falling, it starts to rise faster and faster on its own. That's how strange cosmic expansion is under the influence of dark energy. How much dark energy is there in the universe? Current models suggest that approximately 70% of the cosmos is made up of this enigmatic substance. Only a small fraction corresponds to ordinary matter, the stuff that forms planets, stars, and people. The rest, about 25%, is dark matter, which we also cannot see but can detect through its gravity. In other words, most of the universe is made up of things we cannot observe directly. Isn't it incredibly puzzling to think that what we know is just the tip of the cosmic iceberg? Where does dark energy come from? No one knows for sure. Some theories point to the cosmological constant, an idea proposed by Einstein that suggests that the vacuum of space has an inherent energy. Other hypotheses talk about unknown quantum fields or new physical laws yet to be discovered. What is certain is that dark energy determines the ultimate fate of the universe. If it continues to dominate, the expansion will keep accelerating and galaxies will drift apart until they are isolated in the vastness of emptiness. Thus, dark energy is not only key to understanding the present of the universe, but also its most distant future. Is it possible that the universe, so vast and seemingly unchanging, was ever completely different? The answer is yes. The universe has not always been as we see it today. Its history is one of continuous transformation, from an extremely hot and dense state to the cold, expanding immensity we inhabit. But how do we know that the universe evolves, and what does this evolution really mean? It all begins with expansion. Far from being static, space itself stretches, carrying galaxies and clusters with it, as if they were points on the surface of an inflating balloon. This expansion implies that, in the past, everything was much closer, hotter, and more compact. In fact, if we go back in time, we find a cosmos so dense that the physical laws we know begin to falter. As space has expanded, temperature has decreased, and matter has organized into increasingly complex structures. First atoms, then stars, galaxies, and finally, the clusters and filaments that form the gigantic cosmic web. Has the universe always changed at the same rate? The answer is fascinating. No. Billions of years ago, matter dominated the universe, and expansion was relatively slow. But today, a mysterious component, dark energy, accelerates the expansion at ever-increasing rates. It's as if, after a long uphill walk, the universe suddenly started running downhill without slowing down. This acceleration is one of the greatest enigmas of modern cosmology and suggests that the future of the universe will be even more astonishing than we imagine. During this evolutionary process, stars are born, live, and die, seeding the cosmos with the elements that form planets, atmospheres, and even life. Galaxies collide and merge in gravitational dances that can last billions of years. The Milky Way, our galaxy, is no exception. In the future, it will collide with the Andromeda Galaxy, an event that will completely change the appearance of our cosmic neighborhood. Thus, the universe not only changes, it is in constant creation and destruction, in an endless cycle where each moment is unique and unrepeatable. Where does this journey lead us? Although the physical laws governing cosmic evolution are increasingly well understood, the ultimate fate of the universe remains shrouded in mystery. What is clear is that we live in a dynamic cosmos, in perpetual motion, where every galaxy, every star, and every atom participates in a story of transformation and wonder. The evolution of the universe is not just a matter of large-scale changes, it is the reason we exist and the proof that, in the cosmos, nothing remains the same forever. What was there before the Big Bang? This is one of the most perplexing questions humanity has ever posed. Our intuition leads us to imagine the universe as a stage where, if we go back far enough in time, we could peek into what existed just before that first moment. However, science confronts us with a paradox. According to the Big Bang theory, time and space themselves were born at that moment. Does it make sense to talk about a before when time did not yet exist? Some scientists compare this idea to asking what is north of the North Pole. The very concept of north ceases to make sense at that point. Similarly, the concept of before loses meaning when we talk about the origin of time. Classical physics simply stops at that boundary, as if the universe emerged from absolute nothingness. But what does nothing mean in scientific terms? Is it really a total absence of existence? Or is there something deeper and still unknown? There are several theories that attempt to address the mystery. One of them is the cyclic universe hypothesis, which suggests that our universe could be just one of an infinite series of births and collapses, as if the Big Bang were merely another stage in an eternal cycle of expansion and contraction. Another possibility, proposed by quantum theory, is that the universe emerged from a quantum fluctuation in a primordial vacuum, a kind of quantum foam where the laws of conventional physics do not apply. In this scenario, the Big Bang would not be the absolute beginning, but rather the transition from a quantum state to a classical and observable one. Even more radical ideas have been proposed. For example, the multiverse theory suggests that our universe is just one bubble among many, each born from its own Big Bang, in an infinite ocean of parallel universes. From this perspective, what we consider the beginning could simply be a local event in a much vaster reality. However, so far, all these proposals remain in the realm of speculation, because there is no observational evidence capable of confirming or refuting what existed before, if that concept has any physical meaning. The truth is that at this moment, science cannot definitively answer what was there before the Big Bang. We are faced with one of the current limits of human knowledge. We may never have direct access to that information, or perhaps in the future, we will discover new laws that allow us to go beyond that mysterious threshold. In the meantime, the question remains open, reminding us that the universe, for every answer, gifts us new and fascinating enigmas. What if the Big Bang was not the only origin? What if our universe is nothing more than a solitary bubble in an ocean of parallel realities? The idea of a multiverse, a collection of many universes, has emerged as one of the most fascinating and perplexing questions in modern cosmology. Although it may sound like science fiction, current physics suggests it could be something more than a mere fantasy. Why have scientists begun to take seriously the possibility that other universes exist besides our own? It all starts from the limits of our knowledge. The observable universe has a finite size because light has only had a limited time to reach us since the Big Bang. But what if what we see is just a small region of a reality much vaster, or even of an infinite set of universes, each with its own physical laws? Some theories, like eternal cosmic inflation, propose that space-time could be constantly generating universes, each emerging like a bubble within an expanding cosmos. It's as if our universe is just one bubble in an infinite foam, and each bubble represents a universe with distinct stories, rules, and possibilities. But what are the scientific foundations of these ideas? Quantum mechanics, for example, suggests that there are many ways in which reality could unfold, and each of those ways could correspond to a different universe. At the same time, string theory, which attempts to unify all the forces of nature, predicts the existence of multiple dimensions and possible spaces. Even some mathematical models allow for the existence of universes with different physical constants, where gravity, light, or matter would operate in ways completely unknown to us. In this context, the Big Bang that originated our universe would be just one of many possible Big Bangs happening in different corners of a multiverse. The big question is, will we ever be able to know if other universes exist? For now, the evidence is indirect, based on theories and mathematical extrapolations. There is no way to directly observe another universe, as they would, by definition, be causally disconnected from ours. However, some scientists are exploring the possibility of finding subtle traces, like strange patterns in the cosmic microwave background radiation, that could indicate interactions with other universes in the distant past. It's like searching for the shadow of something we can never see head-on, but whose consequences might be etched in the very fabric of our cosmos. In the end, the notion of a multiverse forces us to rethink our place in reality. If infinite universes exist, each with different stories and laws, what does that mean for the uniqueness of our own universe? Are we just one possibility among many? Or is there something special about the cosmos we inhabit? The search for answers continues, pushing the boundaries of science and our imagination, and reminding us that, deep down, the universe may always be stranger and more fascinating than we ever imagined. What role does entropy play in the future of the universe? To answer this, we first need to understand what entropy really is. In simple terms, entropy is a measure of disorder or randomness in a system. But why is this important for the cosmos? The second law of thermodynamics tells us that over time, the total entropy of a closed system always tends to increase. And the universe, in this sense, can be considered the largest closed system that exists. Every star that goes out, every atom that disintegrates, and every physical process that occurs gradually contributes to increasing universal entropy. Does this mean that everything is doomed to chaos? Not exactly. The increase in entropy does not imply immediate destruction, but rather a gradual process in which useful energy, the kind that can be harnessed to do work, dissipates. Imagine a hot cup of coffee left forgotten on a table. At first, the coffee is full of thermal energy, but over time, that energy disperses into the air and the temperature equalizes with the environment. The universe is undergoing a similar process, but on an unimaginable scale. Eventually, energy will be distributed so evenly that no significant physical processes will be possible anymore. Where does this constant increase in entropy lead us? To one of the most intriguing scenarios, the so-called thermal death of the universe. In this distant future, all matter will be so dispersed and energy so evenly distributed that nothing will occur except random fluctuations of particles. Stars will go out, black holes will evaporate, and the cosmos will be left in a cold, dark state. The structure we know today will disappear, and the universe will become a place where time and change lose their meaning. However, entropy has also been key to the existence of complexity and life. Energy differences, heat flow, and the universe's tendency to evolve toward disorder have allowed galaxies, stars, planets, and ultimately beings capable of questioning the fate of the cosmos to emerge. But the question remains, is this end inevitable? Some theories speculate about quantum fluctuations capable of creating bubbles of order in the vacuum, or about new cosmic cycles. However, with what we know today, entropy seems to be the great director of universal history, marking a destiny in which, ironically, maximum disorder implies the total absence of events. What awaits the universe in the future? This is one of the most fascinating and complex questions in modern cosmology. Scientists have spent decades exploring possible fates for the cosmos, and although we still don't have all the answers, there are several main scenarios supported by observations and theories. The ultimate fate of the universe largely depends on the amount of matter and energy it contains, as well as the mysterious dark energy that seems to drive its accelerated expansion. Will the universe continue to expand forever, or will there come a time when everything stops and collapses? One of the most discussed scenarios is the so-called Big Freeze. If dark energy continues to dominate, the expansion will not only continue but will accelerate even more. In this scenario, galaxies will move away from each other until they are so distant that the light from each can no longer reach the others. Over billions of years, stars will exhaust their fuel, and the universe will become a cold, dark place where only remnants of stars, frozen planets, and lonely black holes will remain. But what if gravity manages to halt the expansion? Then the opposite scenario arises, the Big Crunch. If the density of matter in the universe was sufficiently high, the expansion would slow down until it completely stopped and then reversed. The entire cosmos would begin to contract, galaxies would come closer together, temperatures would rise, and ultimately, all matter and energy would collapse back into an extremely dense and hot state, similar to the starting point of the Big Bang. However, current measurements suggest that this fate is unlikely, as dark energy seems to be in the lead. There is also an even more perplexing possibility, the Big Rip. In this scenario, dark energy would not only accelerate the expansion, but would do so at an increasingly dizzying rate. Eventually, the force of expansion would surpass all known forces, tearing apart galaxies, star systems, planets, and even atoms. In an unimaginably distant future, the very fabric of space-time would be torn apart. Although this idea sounds extreme, some mathematical models consider it plausible if dark energy behaves in an even more exotic way than we imagine. And what is the real probability of each of these futures? Based on current data, the most supported scenario is one of eternal and accelerated expansion, the Big Freeze. But science remains open to new surprises. It all depends on the precise nature of dark energy, a component of the universe that we are just beginning to understand. What we do know is that the fate of the cosmos is tied to fundamental forces that still challenge us, and that the universe, as we know it, will change in astonishing ways on timescales that defy human imagination. Did the universe have a beginning, or has it always existed? This question has fascinated humanity for centuries and has led to various theories about the origin of the cosmos. The Big Bang theory is the most widely accepted today, but what other ideas have competed with it over time? Why do most scientists favor the Big Bang over other alternatives? For much of the 20th century, the main rival to the Big Bang was the steady-state theory. According to this proposal, the universe had no beginning. It has always existed and will always be more or less the same on large scales. To explain the observed expansion, its proponents suggested that as galaxies moved away from each other, new matter spontaneously emerged to fill the gaps, as if the universe were eternally regenerating itself. This idea was appealing because it avoided the uncomfortable question of a beginning, but it had an Achilles heel. It could not explain the existence of cosmic microwave background radiation, or the abundance of light elements like hydrogen and helium. Over time, observations accumulated evidence against the steady state and in favor of the Big Bang. What if the universe did not have a single origin, but goes through infinite cycles of expansion and contraction. This gives rise to the cyclical universe theory. Imagine a cosmos that expands, then contracts to a big crunch, only to start again in a new Big Bang. This model attempts to answer the mystery of why there is something instead of nothing, and suggests that the universe could be eternal in a different sense, undergoing cosmic rebirths. However, current measurements indicate that the expansion of the universe is accelerating, making it unlikely that it will ever contract again, leaving cyclical models in a difficult position to sustain. Another intriguing idea is the quantum steady-state universe model, which combines elements of quantum physics to postulate a universe without beginning or end, where quantum fluctuations create small bubbles of universes, one of which would be ours. Although these proposals are fascinating from a theoretical standpoint, they lack the strong observational evidence that supports the Big Bang. The background radiation, the redshift of galaxies, and the abundance of light elements form a set of clues that other theories simply fail to explain as well. So, why is the Big Bang considered the best explanation so far? Because it brings together the most fundamental observations about the universe under one framework: its expansion, its chemical composition, and the residual thermal imprint of its early moments. This does not mean it is a perfect or definitive theory. Science progresses by questioning and refining its models. However, until new evidence emerges, or an alternative theory explains even more things with equal simplicity, the Big Bang remains the cornerstone for understanding the origin of everything that exists. What evidence do we have that the universe had a violent and hot beginning, known as the Big Bang? Why are scientists so convinced of this theory and not another? To answer, we must look at the traces that the cosmos itself has left behind, like pieces of a gigantic puzzle. The first clue is the expansion of the universe. If we observe distant galaxies, they all seem to be moving away from us. The farther they are, the faster they move away. It's like inflating a balloon, and the points drawn on it are separating more and more. This phenomenon was observed in the 1920s, and not only indicates that space itself is expanding, but that if we go back in time, everything must have been much more concentrated in the past. But how do we know that the universe was really hot and dense in its origins? Here comes one of the most compelling pieces of evidence: the cosmic microwave background radiation. This is a kind of fossil echo of the Big Bang, a faint radiation that fills the cosmos uniformly. It was accidentally detected in 1965 and has since been studied with great precision. Its temperature is just 2.7 degrees above absolute zero, but its existence and characteristics match exactly with the predictions of the Big Bang theory. It's like finding very cold but unmistakable embers from a fire that occurred billions of years ago. And what about the chemical elements? The universe is primarily composed of hydrogen and helium with tiny traces of lithium. But why these elements and not others? The explanation lies in primordial nucleosynthesis. According to calculations, in the first minutes after the cosmic origin, the conditions were so extreme that only light nuclei could form. The exact proportions we observe today, both in distant galaxies and in our immediate surroundings, surprisingly match the mathematical predictions of the Big Bang. If the universe had begun differently, the amounts of helium or lithium would be very different. Finally, the large-scale structure of the universe supports the story told by the Big Bang. Galaxies are not distributed completely randomly, but rather form gigantic filaments and voids, like a cosmic web. The small fluctuations in the cosmic microwave background radiation correspond exactly to the seeds of these structures. It's like reading the rings in a tree trunk and discovering the history of its growth within them. All these independent pieces of evidence, gathered from different corners of science, point to the same origin. The universe had a beginning, and that beginning was the Big Bang. The Big Bang model has managed to explain a huge amount of observations about the universe, but there are still questions that challenge our understanding. Why is the universe so uniform in all directions when, According to the time that has passed since its origin, opposite regions of the cosmos have never been in contact. This is one of the most intriguing mysteries, the cosmic horizon mystery. To resolve it, scientists proposed cosmic inflation, an ultra-rapid expansion in the first moments, but the precise cause of that inflation and its deep nature remain unknown. Another big question lies at the very beginning. What exactly happened at the zero moment? The physics we know ceases to be valid when we reach scales as small as the Planck length, an inconceivably tiny fraction of time and space. There, gravity and quantum mechanics collide, and we do not have a theory that unifies them. Does the before the Big Bang even exist, or did time and space come into being along with the universe? The answer remains hidden, as if the universe is jealously guarding the secrets of its origin. The enigma of dark matter and dark energy is also fundamental. We know they make up most of the cosmos, but what are they really? Dark matter acts like an invisible skeleton that holds galaxies together, while dark energy drives the accelerated expansion of the universe. However, both elude direct detection and challenge our most robust theories. Is it possible that new particles, or even forces, are waiting to be discovered? Each attempt to decipher them opens new doors to the unknown. Finally, the question of the asymmetry between matter and antimatter arises. At the beginning of the universe, they must have been created in equal amounts, but today, almost everything we see is made of matter. Why did matter survive while antimatter practically disappeared? Physics still does not have a definitive explanation for this imbalance. Moreover, the fundamental laws that govern the universe could be different in other corners of the cosmos, or in other universes, if they exist. Thus, each discovery answers one question, but always leaves many others open, ensuring that the exploration of the origin of the universe is far from over. Is it possible to see the past? In astronomy, the answer is yes, and the key lies in the finite speed of light. When we observe a star located 100 light-years away, what we are really seeing is what that star was like 100 years ago. Every glance at the sky is a window to different epochs of the universe, and our telescopes function as true time machines. But how far back can we look? What limits does our cosmic vision have? Technology has been our fundamental ally in unraveling the mysteries of the cosmic past. The first telescopes barely allowed us to distinguish neighboring planets. But the development of increasingly powerful instruments has taken us much further. The Hubble Space Telescope, for example, allowed us to capture galaxies formed over 13 billion years ago. However, the real leap came with telescopes that can capture wavelengths invisible to the human eye, such as radio telescopes and microwave detectors. Thanks to them, we have been able to detect the cosmic microwave background radiation, the fossil echo of the early universe, emitted when the cosmos was only 380,000 years old. But the search doesn't end there. How do we manage to observe the first moments after the Big Bang, when the universe was opaque and light could not travel freely? Here, even more sophisticated technologies come into play. Gamma-ray telescopes and neutrino detectors seek signals that have managed to penetrate that initial veil. Even gravitational wave observatories, like LIGO and Virgo, open a completely new window to the past, capturing ripples in space-time generated by collisions of black holes or neutron stars. These waves travel unabsorbed, allowing us to receive direct messages from events that occurred billions of years ago. Technological advancement continues, and the questions multiply. Will we ever be able to detect the light from the first stars, or even trace signals predating the cosmic background radiation? The James Webb Space Telescope, for example, is already pushing the boundaries of what is observable, allowing us to study galaxies formed just a few 100 million years after the Big Bang. Each new instrument is a key to unlocking unprecedented chapters of the universe's history, and although we will never be able to see the very initial moment, each discovery brings us a little closer to understanding how it all began. Thus, telescopes and technology not only show us the cosmos, but also connect us directly with the origin of time and matter. Is it possible that the strangest rules of the universe dominated its earliest moments? Quantum physics, that set of laws governing the behavior of the tiny, played a central role in the beginning of the cosmos. While in our daily lives we are used to things having defined positions and trajectories, in the newly born universe, those certainties simply did not exist. At extremely small scales, much smaller than the size of an atom, reality becomes blurry, almost as if particles could be in many places at once. But why does this matter for the origin of the universe? When the universe was younger than a fraction of a second, there were no planets, stars, or even atoms. There was only a kind of quantum foam, a sea of probabilities where energy fluctuations appeared and disappeared constantly. These fluctuations, though tiny, sowed the seeds of everything that exists today: galaxies, stars, even us. It's as if, by rolling the dice in the quantum roulette, each possible outcome left a mark, an imprint, that millions of years later would become clusters of galaxies and vast cosmic voids. Isn't it astonishing to think that the microscopic imperfections of that primordial chaos shaped the giant structure of the universe? But how can something so small and so random affect the entire universe? This is where quantum mechanics challenges our intuition. For example, the uncertainty principle states that you cannot know both the energy and the time of a system exactly at the same time in those early moments. This allowed brief bursts of energy to arise from nothing, which then influenced the distribution of matter and energy as the universe expanded. Those quantum flashes, amplified by processes like cosmic inflation, became the density differences we see today when we observe the cosmic microwave background. In other words, the current universe is a gigantic reflection of the unpredictable rules of quantum physics. And how far can the influence of the quantum extend? Although gravity dominates on a large scale, in the primitive universe, the rules of the subatomic world determine the fate of everything we know. Today, scientists are trying to unite quantum physics with gravity to accurately understand how the universe was born. It is a monumental challenge to bring together the infinitely small and the infinitely large into a single theory. For now, what we know is that without quantum physics, the universe as we know it simply would not exist. The strangest rules of nature were in fact the architects of everything. What happens when we try to unite the rules of the smallest with those of the largest? In the universe, there are two fundamental pillars of physics: quantum mechanics, which describes the behavior of subatomic particles, and general relativity, which explains how gravity and space-time work on a large scale. But there is a place where these two theories collide: the singularity of the Big Bang, that mysterious point where the entire universe was compressed into infinite density and an almost zero volume. How can we understand that moment when known laws cease to function? The singularity is, in essence, the best-kept secret of the cosmos. According to general relativity, if we keep going back in time, the entire universe contracts until it reaches a point of infinite density and unimaginable temperature. But something fascinating happens here. Einstein's equations break down as if we were trying to divide by zero. It is at that moment when quantum physics should take control, since at tiny scales, the behavior of space and time can no longer be described by classical gravity. However, to this day, there is no complete theory that unifies gravity with quantum laws. What would a theory of quantum gravity look like? Imagine that space-time is not a smooth and continuous fabric, but rather a kind of microscopic network made up of tiny grains, or atoms, of space and time. As we approach the singularity, these quantum grains could prevent the density and temperature of the universe from becoming truly infinite. Proposals like loop quantum gravity and string theory attempt to describe this fundamental structure, suggesting that, instead of an absolute beginning, there may have been a quantum bounce, or that time and space themselves emerge from even more basic processes. The search for quantum gravity is one of the greatest challenges of modern physics. Solving this enigma would not only help us understand the true origin of the universe, but also extreme phenomena like black holes and the ultimate fate of the cosmos. Are we close to finding an answer? Physicists are exploring new mathematics, experiments, and observations of the early universe, seeking clues in the cosmic microwave background or in gravitational waves. However, for now, the singularity remains a frontier, a reminder that, although we have made significant progress, the universe still holds secrets waiting to be uncovered. What makes particles have mass? It is one of the most fundamental questions in physics. Without mass, atoms wouldn't exist. There would be no planets, no stars, no galaxies. But where does mass really come from? The answer leads us to one of the most intriguing pieces of the cosmic puzzle: the Higgs boson. The Higgs boson is an elementary particle predicted by the Standard Model of Physics and confirmed in 2012 thanks to the Large Hadron Collider. But its true role is even more fascinating. To understand it, imagine the universe as a dance floor and all the particles as dancers. Most move easily, but some seem to stumble or move slowly. The secret lies in the floor of the dance floor, an invisible field called the Higgs field. Particles that interact a lot with this field move more slowly, as if they are dancing on a sticky floor, and that is what we perceive as mass. But why is this mechanism so crucial? Before the Higgs field made its appearance, all particles were like beams of light, massless, unable to come together to form matter as we know it. It was only a fraction of a second after the origin of the universe when the Higgs field turned on, filling space and allowing particles to acquire mass. Without this process, the universe would be a radically different place, lacking complex structures and, of course, lacking life. The discovery of the Higgs boson was like finding the missing piece in a complicated puzzle. Although the boson is just a manifestation of the Higgs field, its existence confirms that this field is indeed there, acting constantly throughout the universe. Physicists call it the giver of mass, because without it, protons, neutrons, and electrons would be weightless particles, unable to form the atoms that make up everything we see. Does this mean that the Higgs boson is responsible for all the mass in the universe? Interestingly, not entirely. Most of the mass of protons and neutrons comes from the energy of the forces that bind quarks together inside them, not directly from the Higgs field. But it is the Higgs field that gives mass to quarks and electrons, allowing everything else to happen. Without this cosmic signature, matter as we know it simply wouldn't exist. Thus, the Higgs boson is much more than a particle. It is the key that makes a universe with structure, complexity, and ultimately, with us questioning its origin possible. What does it really mean for the universe to be symmetrical? Symmetry, in physics, refers to the idea that certain properties remain unchanged, even if we alter something in the system. For example, if you throw a ball into the air, the laws governing it do not change whether you do it during the day or at night. This invariance is a temporal symmetry. Now, imagine that the universe, in its earliest moments, was like a perfect mirror where all forces and particles were indistinguishable, as if you were watching a game where all the pieces are identical and the rules are exactly the same for everyone. But why do different forces and particles exist today, and why does matter dominate over antimatter? The key lies in a phenomenon called symmetry breaking. It's as if, suddenly, that perfect game became unbalanced and one piece decided to break the rules, changing the fate of the entire board. In the early moments after the birth of the cosmos, the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak force, were unified. But as the universe expanded and cooled, these symmetries spontaneously broke, separating the forces and allowing for the complex variety of particles we know today. It's a bit like when water freezes and from a homogeneous liquid, a crystal with unique patterns emerges. But how does this affect our existence? Without symmetry breaking, there would be no variety. There would be no atoms, no stars, no planets. All the components of the universe would be identical, and cosmic evolution would be impossible. It is this breaking that allowed, for example, the Higgs field to give mass to particles and for matter to prevail over antimatter. Physicists are still studying how small asymmetries in the fundamental laws led to a universe dominated by matter. If symmetry had not been broken, we could live in a cosmos where light and matter would not be distinguishable, and reality, as we know it, would not exist. Can a fundamental symmetry break again in the future? No one knows. The truth is that the current universe bears the marks of that crucial moment when perfect symmetry shattered. It is one of the great mysteries of physics, how from such a uniform initial situation emerged the diversity that makes everything possible, from galaxies to ourselves. Symmetry breaking is the spark that ignited the complexity of the cosmos, showing that sometimes beauty arises precisely when balance is disrupted. What if at the beginning of the universe, every particle of matter had an antimatter twin? According to known physical laws, every time a particle emerges, its counterpart should also appear. The electron and the positron, the proton and the antiproton. When matter and antimatter meet, they annihilate each other in a flash of pure energy. Yet here we are, in a universe almost entirely composed of matter, with antimatter relegated to a rarity in laboratories and cosmic collisions. Why isn't the cosmos just a gigantic explosion of energy, the result of total annihilation between the two? This question is one of the greatest mysteries of cosmology, the cosmic asymmetry between matter and antimatter. If in the early moments of the universe both emerged in identical amounts, what tipped the scales in favor of matter? Physicists call this the violation of CP symmetry, a rule that, in theory, should have maintained balance, but for some reason, it did not. In simple terms, the universe acted slightly differently with matter than with antimatter. But the difference was minuscule. For every 10 billion matter-antimatter pairs, only one particle of matter survived. All the others were annihilated, leaving behind the material universe we know. How do we know that antimatter exists, and why is it so difficult to find it today? In experiments at particle accelerators, such as the Large Hadron Collider, scientists can create antiparticles and observe how they behave. For example, the positron, the antiparticle of the electron, is even used in medicine, in techniques like positron emission tomography. But the artificially created antimatter disappears almost immediately upon encountering normal matter. Additionally, in cosmic rays bombarding the Earth, antimatter particles are occasionally detected, but never in sufficient quantities to suggest that there are galaxies made entirely of antimatter. Could there be regions of the universe where antimatter dominates, hidden beyond our reach? So far, all observations suggest otherwise. If they existed, we would expect to see unmistakable signals of annihilation at the edges where matter and antimatter would meet, releasing enormous amounts of radiation. But the sky is silent on that front. The asymmetry seems universal. Our universe is a place where, for reasons still unknown, matter triumphed over its inverse twin. This slight preference for matter over antimatter is the reason galaxies, stars, planets, and we ourselves exist. If symmetry had been perfect, there would be nothing but light. Solving the enigma of cosmic asymmetry is not just a matter of fundamental physics, but also points to the very root of our existence. Why is there something instead of nothing? The answer, still hidden, could revolutionize our understanding of the universe and our own origin. How big is the universe? If we tried to answer that question, we would encounter figures that defy our imagination. The observable universe spans approximately 93 billion light-years in diameter. That means that, although light travels very fast, it would take more than 46 billion years just to go from Earth to the edge of the visible universe in one direction. And that's only considering the part of the universe we can observe. It is suspected that the total universe could be much larger, even infinite. Now, how many stars are out there? Astronomers estimate that there are at least 100 billion galaxies in the observable universe, and each one can contain between 100 billion and 1 trillion stars. If you tried to count all the stars in the observable universe, saying one number per second, you would need many times the current age of the universe to finish. To put it in perspective, there are more stars in the known universe than grains of sand on all the beaches of Earth. And what about the age of the universe? According to the most precise measurements, the universe is about 13.8 billion years old. To give us an idea of this timescale, if we condensed all of the universe's history into a single year, modern humans would have appeared only in the last minutes of December 31st. Everything we consider human history would be just a blink in that cosmic calendar. As for the temperature, the universe has gone from unimaginably high temperatures right after the Big Bang at nearly 300 billion degrees to gradually cooling down. Today, the average temperature of deep space, known as the cosmic microwave background radiation, is about 2.7 degrees above absolute zero. That is much colder than any earthly winter, so cold that most molecules would remain motionless. Visible matter, everything we can see and touch, represents only about 5% of the total mass and energy of the universe. The rest is made up of dark matter and dark energy, two mysteries that still challenge us. And if you're wondering how empty space is, consider this. In the emptiest region of the universe, there are fewer than 1 atom per cubic meter, which means that if we take a single breath, we inhale more particles than there are in thousands of cubic kilometers of intergalactic space. Finally, did you know that the light we see from the farthest galaxies left there when Earth didn't even exist? Some of those galaxies show us their light as it was over 13 billion years ago. Thus, every time we observe the universe, we not only see immense distances, but also travel back in time to the very origins of everything we know. The universe, in numbers, is the greatest reminder of our smallness and, at the same time, of the grandeur of the cosmos to which we belong. Why can a scientific theory about the birth of the universe change our way of seeing the world and ourselves? The Big Bang not only revolutionized physics and astronomy, it triggered a genuine philosophical and cultural revolution. Before its emergence, many cultures believed in an eternal cosmos, or in infinite cycles of creation and destruction. However, the idea of a universe with a specific beginning, a moment in time when everything started, forces us to rethink fundamental questions. Why is there something instead of nothing? Is the universe an accident, or does it have a purpose? This paradigm shift even affected the way we conceive our place in the cosmos. If the universe had a beginning, it also has a history, a development, and perhaps an end. We are part of a cosmic narrative with a distant past and an uncertain future. Humanity, in this context, moves from occupying the center of the universe to being the result of physical processes that date back billions of years. This perspective may make us feel tiny, but it also connects us with everything that exists. Every atom in our body arose from events that began at that primordial instant. The Big Bang theory also challenged and enriched the debates between science and religion. Some traditions saw in the origin of the universe an unexpected compatibility with creation stories, while others experienced tension when facing a purely physical explanation of the cosmos. Can science answer the ultimate questions about meaning and purpose? Or will those inquiries always remain beyond the limits of observation and experiment? The Big Bang has not resolved these dilemmas, but it has placed them at the center of contemporary intellectual and spiritual debate. Finally, the cultural impact of the Big Bang extends to art, literature, and the collective imagination. The concept has inspired novels, movies, music, and even everyday metaphors about beginnings and endings. It invites us to think of the universe as a dynamic and ever-changing stage, not as a static backdrop. Is it possible that by understanding how everything originated, we also better understand who we are and what it means to exist? The true power of the Big Bang may not lie solely in its scientific explanation, but in the way it continues to expand the boundaries of our curiosity and wonder. Where do we really come from? Are we the result of a mere cosmic coincidence, Or is there a profound purpose behind the existence of the universe? Looking at the origin of the cosmos is like trying to read the first pages of a book whose cover was lost in an explosion of light and energy. Everything we are, every atom in our body, every star in the sky, comes from an unimaginably small and dense moment, an initial spark that, in a fraction of a second, changed everything. The universe, in its essence, was born from an explosion so colossal that even today, billions of years later, we still feel its echo in the darkness of space. But how do we know that all of this is not just another theory? Science has managed to capture the traces of that birth. The continuous expansion of space, the distant whisper of background radiation, the precise abundance of light elements, and the very structure of galaxies and clusters. Each observed piece of evidence is like a piece of a gigantic puzzle, revealing not only how everything began, but also how it evolved into the universe we inhabit. Still, the more pieces we fit together, the more questions emerge from the shadows. Why is there more matter than antimatter? Where do dark matter and dark energy come from? Those mysterious forces that dominate the cosmos, yet remain almost invisible. Thinking about the Big Bang confronts us with the limits of human knowledge. What was there before? Does the very notion of before make sense when we talk about the origin of time and space? For now, science can only speculate, and each answer seems to open the door to new enigmas. Sometimes, understanding the universe is like trying to catch the wind with our hands. The more we learn, the more we realize how much we have yet to discover. However, this mystery is not a cause for frustration, but for wonder. The fact that we can ask ourselves these questions, that our minds can travel to the edges of time, is a testament to the power of human curiosity. Thus, the origin of everything remains one of the greatest intellectual challenges of our species. The universe is a constantly changing stage, a story that is still being written and in which we are all protagonists. The quest for answers about the birth of the cosmos speaks not only of distant stars and galaxies, but also of ourselves, our place in the infinite, and the eternal adventure of trying to understand it all. Perhaps we will never have all the answers, but as long as there are questions, the journey will continue. What if the greatest secret of the universe is not its origin, but our ability to be amazed by its existence?